Hi, I'm Andy. I'm from ETH Zurich. I'm part of a group from ETH Zurich and from the University of Bologna under the lead of Professor Luca Benini. We are around 40 people working on the so-called PULP project, where PULPino is an offspring of. We have a lot of close collaborations for those projects with, for example, the Politecnico di Milano, CEA, LETI, EPFL. We also have support from industry, from ST Microelectronics, which gives us access to the 28 nanometer FD-SOI technology, and they allow us to tape out test chips in their technology. So a little bit about what we do is we care about computing for the Internet of Things. In this stuff, you have sensor input. For example, you have microphones, you have thermal sensors, you have cameras, you have whatever sensor input, which consumes about 100 microwatts to about, let's say, 2 milliwatts. This then gets consumed by a microcontroller, which is something like a Cortex-M class, which consumes between 1 and 10 milliwatts and delivers about 1 to 25 mega operations per second. Then, as part of your algorithm, to do something useful with the sensor data that you acquisitioned, you have to transmit it to a host, which executes a more complex algorithm. Then transmitting this uses even more energy. If it's active, it uses, let's say, 50 milliwatts. This becomes a problem if you're using something battery-powered or you're even using energy harvesting, and the power envelope that you have is just a few milliwatts. So our idea is to transition more of the algorithm to the microcontroller and use something like a parallel ultra-low power processor that allows you to have like 2 giga operations per second in the same power envelope as a classical Cortex-M CPU. The way you want to do that is using PULP, which is a parallel ultra-low power processor which exploits parallelism. What we do is we use multiple small and simple cores organized in clusters. For example, up to 16 cores that are organized in one cluster. Inside the cluster you have shared instruction cache, and you have shared scratchpad that all cores can access. Then you instantiate multiple of those clusters and put them on a chip, so you can scale to hundreds of cores for a single system. Every core in there is very simple and based currently on OpenRISC, which is what we started out with. And we are now looking into the transition to RISC-V and to compare our OpenRISC-based cores with RISC-V-based cores. To further enhance energy efficiency, which is our primary goal, we are also looking into extending the RISC-V ISA to add more instructions that help our algorithms that we are interested in. As a further energy reduction method, we are using dedicated accelerators for applications. And to really go to ultra-low power, we're using near-threshold operation, meaning that we lower the voltage of the core as far as possible, going to like 0.54 volts. And just we lower it as much as possible so that we still meet our performance goals. In terms of chips that we have taped out inside these projects, there are many. We have the main PULP series, which consist of PULP V1, V2, V3, and so on, which are taped out in ST28 nanometers FD-SOI technology. Then we have building blocks where we try out new things like integrating an FPU, you're looking into approximate computing, trying out new features for a cluster. Those are usually taped out in UMC65. And we also taped out our first RISC-V-based cluster, which we call Honey Bunny, which is a joke on Pulp Fiction. And this was taped out in GlobalFoundries 28 nanometers. We want to open source our effort in building this PULP system, but the PULP project is very huge. It's really a lot of IPs that we have developed for it. I mean, there are peripherals, there's the instruction cache, there are interconnects, there is the whole AXI bus, there is the cores, there is a software framework for OpenMP, for OpenVX. We have our custom tool set, we have a virtual platform, and so on and so on. It's really very big. So we thought it's not a good idea to open up everything at the same time, but to start out with something simple that everyone understands, which is PULPino. This is something we created especially for this purpose. It is focused on being simple, so it is a minimal system just to showcase our core and to open up the core plus some basic set of peripherals and the buses. It's also a single core thing compared to the many core platform that we're developing, which is something that our partners had a huge demand of because they would like to see the core and use it for other purposes, but they sometimes don't care about the whole multi-core stuff around it. So PULPino could be described as a microcontroller style platform. It's focused on the core. There are no caches. There is no memory hierarchy. There is no DMA. All IPs are reused from the PULP project. We didn't have to write any new IPs for the whole thing. PULPino is available for RTL simulation. We have it available as an emulator for FPGA, and we're working on the first ASIC tape-out for the end of January. This tape-out is done as a student project, as was also mentioned yesterday by Florian Zauerba, which is also here. And it will be in UMC 65 nanometers technology. Now let's build up PULPino. So just to show you what the rationale behind the system is. As I said, it consists of basically the core, and we connected the core directly to two RAMs. First, the instruction RAM and the data RAM. Those RAMs are directly connected, meaning single cycle access, no wait states, really an optimal system in terms of performance because you have no stalls waiting for memories. Those RAMs can be multi-banked RAMs for ASICs, it can be block RAMs, whatever you have available in your technology. But I'd like to note that it's single port, meaning that it's also very efficient from an ASIC standpoint. Then to make things interesting, we have added a central AXI interconnect that allows you to access the two RAMs and also allows the core to access the interconnect. Still, the RAMs are multiplexed between the bus tab from AXI and the bus tab from the core, meaning they're still single port RAMs. To communicate with the outside world, we have added a simple set of peripherals, meaning GPIO, UART, I2C, and SPI. And we have implemented fine-grained clock gating for those peripherals, meaning that you can shut them down if you don't need them, which helps in energy efficiency. Since our peripheral bus is based on APB, that means that you can use any kind of standard components that you have as long as it's compatible with either APB or AXI, which makes it easy for you to extend it if you want to. To be able to shut down the core when it's inactive, we have added an event unit, which is something very simple that just waits for events or interrupts coming from a peripheral, and while the core itself is clock gated. So as soon as an event or interrupt comes, the core wakes up, performs computation, and as soon as it's done, shuts down again, waits for the next event until your application is complete. To be able to access the whole system from the outside world, there is an SPI slave that has access to the whole memory map of the system. Then to debug the system and to provide a JTAG port as well, we have added the advanced debug unit that also Richard has been using for his projects. We ported it from OpenRISC to RISC-V, which was kind of easy because we already had our OpenRISC cores and we're using it there. So it was kind of natural to just port it over to RISC-V and it wasn't a big deal in the end. So now we have two units that allow us to control the whole system because we can access everything inside the PULPino system via SPI or via JTAG. Now, we also want to be able to use the whole system as a standalone chip, because we are fabricating an ASIC and we want to put it on a board and just let it run without anyone controlling it, so really as a real microcontroller. To do that, we have added a boot ROM that contains a very simple bootloader that just loads a program from an external SPI flash. The rationale behind this is we don't have access to a flash inside the technologies we're using. So in terms of FPGA emulation, we are using a ZedBoard, which is very big compared to PULPino itself. PULPino fills like 10% of the LUTs inside the ZedBoard. And what I like to note is that we connect just the interfaces that also the final ASIC will have. So meaning SPI, UART, JTAG, and GPIO. So later on, as soon as we have a fabricated ASIC, we can just swap out PULPino and take everything routed to pins, plug in the ASIC, and use the same framework that we have developed for the FPGA. We can even use the same programs that we wrote for the FPGA first. About how we build and run everything on this system, it's based on CMake, which means that you can just type very simple commands like make program point.fpga, and it gets run on the FPGA. You can type make program point vsim, which starts model sim and runs the RTS simulation. And as soon as we have an ASIC, we will introduce a new target like make program.asic. All of those targets use the same executable, meaning that they're all completely compatible, and there's no difference between RTS simulation, FPGA, or ASIC. It's really, really similar. A little bit behind why are we now switching to RISC-V or considering it. When we learned about RISC-V, it sounded like a very interesting ISA, and we wanted to evaluate it in comparison to OpenRISC. The reason behind this is that RISC-V is much more modern than OpenRISC. For example, it does not have a set flag instruction, which prepares branches in OpenRISC. Similarly, there's also no delay slot in RISC-V compared to OpenRISC, meaning that for a classical branch instruction, while you had to have 3 instructions in total in OpenRISC, RISC-V just uses 1. And if you care about energy efficiency, having less instructions is better, of course. Another very interesting thing is compressed instructions, which also, since we're interested in energy efficiency, is interesting to us because it reduces, again, the pressure on the instruction caches and on the instruction RAM. And you have to fetch less data from the RAMs, which is very expensive. Another thing is RISC-V was designed to be easily extendable, which is what we want to do. Our goals are to have very energy efficient signal processing, and the way we want to do this is to tune the core microarchitecture and also the ISA towards this. So we want to really optimize the whole flow from top to bottom, starting from the way you write applications through compilers, through the ISA, down to the actual ASIC implementations. This means that we want to have extensions to the basic ISA that have a very low overhead in terms of area and power when they are not in active use. Because when you add extensions that are only useful for signal processing and you have an application that doesn't do much signal processing, you would waste energy, which is not what we want to have. So what we added is simple extensions, for example, hardware loops, post-incrementing load and store instructions, a multiply accumulate instruction, and certain ALU extensions that allow you to do common operation in just one cycle, for example, minimum, maximum, absolute value, average value computations. And this helps you a lot for certain applications. So what are hardware loops? Consider a very simple vector addition. I know it's a silly example, but it shows the point. So you have an array A, you want to add 1 to it and save it in the array D. If you're looking at the left-hand side, you see RISC-V assembly code showing that it needs 7 instructions to perform this operation. Also, you have a branch at the end, meaning that you have to pay the branch cost. And depending on your implementation, this can be quite costly because you have to jump and cannot really keep the pipeline filled. If you're now using hardware loops, this means that you can set up the number of iterations beforehand. And you can say like, okay, my loop ends here and it starts here. So you can also anticipate when you have to branch beforehand, which makes it very fast. And you can save 2 instructions because you don't have to do the branch and you don't have to keep the loop pointer. Then the next extension that is very interesting is post-incrementing load and store instructions, which means that you can load something from memory and at the same time increment the address that you use to load something from memory. The rationale behind this is, again, when you have very small kernels with a known number of iterations, with a known pattern, you can get rid of the changing of the loop pointers. So you can go down from 5 instructions from the loop body down to just 3 instructions, meaning that you can save 4 instructions plus the branch cost. We have implemented our own core to do this, which we call RISCY. Sven Stucki already introduced it at the last RISC-V workshop. The core supports full RI5CY. It has partial support for RI32M. Basically, it just implements the null instruction. I guess you have all seen that before. It's just the instruction that is most interesting to us. What I like to stress out is that we have implemented single cycle multiplication compared to Z-scale, which has this bit serial multiplication, but is smaller, of course. We have support for compressed instructions, and we have also support for the ISA extensions, as I was mentioning before. In terms of features, it has interrupts vectorized on 32 lines. We have events, which is kind of interrupts light. So it just say like, I want to wait until something happens, core shuts down, and the event unit tells it like, okay, something has been going on, please wake up and perform this. We have support for exceptions, like illegal instruction exceptions and illegal memory access. We have support for debug, especially software breakpoints, and we provide access to all registers in the system. Also, we have added a simple performance counters that tell you like so many instructions have been executed, so many of them have been compressed instructions, so many taken branches have we seen, so many non-taken branches. Just basic information that helps you in debugging your code and in profiling it. This is a block diagram of the core. It's very simple, based on a 4-stage in-order core. We have the classical pipeline stations, instruction fetch, where we have a prefetch buffer with up to 3 entries. We have instruction decode, where there's also the general purpose register file. We have execute, where we have the multiplication and ALU and the CSR registers. And we have the write back stage that contains the load store unit. In terms of interfaces, we try to be very generic. So we used a simple request ground protocol. This means that we support variable latency systems. For example, we can hook it up directly to an SRAM, or we can hook it up to an AXI bus, and it works for all of those cases, which is great, because this gives you the freedom to hook it up to any kind of system you have in mind. So this was about the data interface. The instruction interface is identical to the data interface, except it's read-only, because it's a simple core. There's no need to write anything over the instruction interface. The debug interface we're providing is aligned with the advanced debug bridge, which just makes it very simple to use the advanced debug bridge for debugging. In terms of performance, what we did is we did a simple comparison between a Cortex-M4 CPU, Orion, which is our OpenRISC-based CPU, and RISC-V, which is the RISC-V-based CPU. First, we compare the base instruction sets. So really just RISC-V versus OpenRISC without the extensions that we have developed. As you can see, they are not so different after all. RISC-V is sometimes faster, OpenRISC is sometimes faster, but overall they are similar. When we start adding our extensions to it, Orion is a little bit more mature. We are working on this core for about 1 or 2 years, so there's also more extensions and better compiler support. While for RISC-V, this is just something we finished like a couple of weeks ago. But all our extensions are supported by our GCC implementation and are inferred automatically. So we did not change anything inside the code to use those new extensions. As you can see, now RISC-V is almost at the same speed as Orion, which means that for us it would be interesting to switch. In terms of area and dynamic power that the core uses, again, we have performed a comparison between RISC-V and the Cortex-M4. Our core is a little bit more efficient than the Cortex-M4 and also is a little bit smaller. In terms of critical path lengths, we have used UMC65 for this comparison. So the internal path means just the longest path that we have inside of the core without going to memory, because usually memory access is what slows you down in very simple SoCs. So we have just 1.15 nanoseconds as an internal path, meaning we can go to more than 800 megahertz. On the memory request side, we have 0.6 nanoseconds delay added by the core. And on the response side, we have 0.4 nanoseconds of delay added. This means that if you have fast memories, you can go to more than 800 megahertz on the UMC 65 nanometer technology. When we're looking at the area of both PULPino, so the whole SoC, and RISC-V, our core, you can see that RISC-V itself is very tiny. It's just 7% of the area of an SoC that contains 32 kilobytes of instruction RAM and 32 kilobytes of data RAM. As you can see, RAM is both 38% of the area, meaning that if you're looking at the floor plan of the chip, it's basically RAM and a little bit of dynamo logic. Inside the core, the thing that consumes most area is the register file. I guess most of you are not very surprised about this. The next thing is the multiplier, which is also not surprising because 32 bits times 32 bits with a 32-bit result. That's just quite big. And the next biggest thing is the prefetch buffer with 3 entries. In total, the core consumes only 35 kilogates, which, as I was saying, is tiny compared to a whole SoC. And especially in the multi-core setting, the cores really are not that big compared to the whole system around it. As I was saying, we want to release this as open source. What we release is the complete PULPino RTL source, so everything we have. So anyone who wants to use this can then tape this out as an ASIC, put it on an FPGA, use it in your simulator, whatever you want to do with it. We include the RISCY Core, we include all IPs. We also include the FPGA build flow, the simulation and build infrastructure that we have developed for software. And we also release free RTOS boards that we have done as part of the student project. The license we are going to use will be SolderPad, which is the same license as far as I know that Low-Risk will be using. And technically, we're ready to release this as open source now. But we have to wait for the final approval from the head of our university. So this may take a couple of weeks now, but I'm sure it will be up on GitHub by the end of the month, probably earlier. I will send an email to the HW dev list as soon as we're ready. So, summing up, PULP is the energy-efficient many-core SoC that we are working on and that we eventually want to open up to the world. But as a first step, we open up PULPino, so just a single-core SoC. It is a complete system that can easily be employed in various projects, especially if you're not interested in building a whole SoC, but just want to build a component for whatever you have in mind, you can do that with this system. It is easily extendable. It is ready to use for any kind of educational purposes that you have in mind. For example, if you want to develop a peripheral in one of your lectures, you can then do that. RISC-V, the core I've developed, is small and optimized for our use case. That means energy efficiency. What are we going to do in the future? So first thing, tape out by the end of the month. Then we are looking into porting PULPino to IPexact, which is a description language kind of that allows you to just click together a whole SoC, which makes it even easier to extend the system and to make it configurable. In terms of features that we want to add to our core, what we are looking at currently is floating point support. This is already available for our OpenRISC course, so it's not a big deal to port it over, but we didn't have time yet. Then we want to add branch prediction, and we are working on evaluating further non-standard ISA extensions, especially the ones that we've already done for our OpenRISC core, and we are trying now to integrate this into the RISC-V world in the most efficient way we can think about. Okay, so that was it. Thanks for your attention.
Okay, it's Martin Schöberl from Technical University of Denmark. I have a question on your first slides on your PULP project. You mentioned you have clusters with 16 cores and sharing instruction cache. How does this work, sharing instruction cache with 16 cores?
It's a multi-banked cache, meaning that not all requests are going to just one instruction cache bank, or they are distributed to the multiple cache banks. Then also we have 128-bit cache lines, which are transferred into an L0 buffer that also reduces pressure on the actual instruction cache. So every time when you fetch an instruction, you're actually getting at least 4 instructions, and you only have to do the next fetch 4 instruction cycles later.
Okay, is it a single cycle arbitration and loading from the cache?
Can you say again, please?
Is it a single cycle arbitration and loading from this cache for the 16 cores?
Yes.
So is this a critical path of your design?
Sorry, I didn't get that.
So is this a critical path of your design?
Sorry, I still didn't get it.
Is it a critical path?
Yes, it's also on the critical path. Thanks. The critical path, in fact, is balanced between the instruction cache and the scratch pad. Also, the scratch pad is multi-banked, and we were working on really making the critical path to the instruction cache and to our data memory as equal as possible. At the same time, for our OpenRISC core, we managed to make it's the same as the internal path inside the core, so we can really say we have a well-balanced system.
How many banks?
It depends on the number of cores that you have. Mostly we're using 4 cores inside a cluster. There we have 4 banks. For 16, I actually don't remember what we have.
On a related note, so your load with increment instruction generates 2 results. Do you have 2 write ports on your register file?
Yes.
How's that going to work out in FPGA?
It works. It's not very efficient, but it works.
Second question was, your cores, how do they communicate? Is the only way to communicate between the cores going through the shared memory, or do you have a network on chip?
The only way to communicate is the shared memory. But I mean, there's also kind of an out-of-band communication via the event unit framework. I didn't mention this here because I wanted to focus on PULPino. PULP has a quite sophisticated event framework that allows every core to trigger events that get propagated to the other cores, telling it like, for example, in OpenMP. I'm done with computation, so I'm shutting down now. If you have a new task, tell me. Something like this. But our plan is really to keep it as simple as possible, which is why we don't have a NOC, but really rely on shared memory for sharing tasks and communicating between the cores.
I had a question about the ISA extensions that you've made already. So RISC-V, for example, with branches, if they're negative, it always says predict them taken, right, for loops. So are there things that you have learned that you want to feed back into the core ISA spec? Are there extensions you want to propose that just become part of the standard spec?
I don't know, honestly. I mean, if there's interest in the RISC-V community to have something like a hardware loop, then we will be very open, of course, to tell you about our experience, what we learned, and what we think is a good spec. I mean, as far as I understood, it's not something that you want to have in a big out-of-order core. The base ISA, in my opinion, is very nice, works very well, and satisfies most requirements. It's just for really our application that we're looking at that we want to have something that makes small cores easier and faster. So, for example, what we're interested in is the B extension. And I guess we can collaborate on this and start to add something that really has nice and useful bit manipulations.
Because one more thing, I'm thinking you could have both in the sense that you could have loop hints, right? This loop probably executes 100 times, and it might not actually do anything on real hardware.
Sorry, say again, please.
So you could have a kind of hint concept, right, where you say this loop is going to take this many cycles, and if you choose not to implement that, you're going to have no loss of performance. But you could provide that kind of level of there are 100 iterations here as a hint that could optionally be.
I see what you mean. Yeah, that would be very interesting, of course. Yes, I mean, if that's something that the community is interested in, I mean, it would be perfect for us. I mean, having something standardized helps us a lot, of course, because it's not our goal to really go away from what is already there. The more that we can share with the community, the better for us. So if that's something that's of interest, yeah, sure, let's do it.
The branch was something we've been thinking about a lot.
This is concerning the loop setup instruction. It's and how it behaves in the context of interrupts. Because you mentioned that you have 32 interrupt inputs. What happens when an interrupt fires after the loop setup instruction, but prior to a completion of a loop iteration? Is there some hidden state that is accessible to supervisor that allows you to restore that?
Yeah, exactly. It's exactly like this. There's a kind of hidden state. I mean, it's just mapped to CSR registers. You can access the current state of the hardware loop, like where does it start, where does it end, how many iterations are still to go, and you can save that on your stack, then jump to the interrupt handler, perform your computation, and jump back.
Does your hardware loop support embedded loops?
What loops?
Your hardware loop does that support embedded loops, so a loop inside another loop?
Yes, we support up to two nested loops. I mean, the limitation there is you have to think about how many registers do you want to spend, because registers are quite expensive. So what we support right now is we support 2 levels of nested loops, which is, we did some exploration in this field and looked at a lot of benchmarks. We tried between 1 and 4 levels of hardware loops, and it seems that 2 levels is the best you can achieve in terms of efficiency, because the hardware overhead is okay, and the performance gain is the biggest, because, I mean, you're not gaining so much in the end compared to having branches. It's just, it helps you most when the loop body is very small, but the more levels you add, the bigger your loop body gets.
I think you mentioned that you wanted to build a branch predictor.
Yes.
What's the motivation for that? What are you expecting to gain there?
The motivation behind the branch predictor is that currently we lose 2 cycles when a branch is taken. Because, let's look at the block diagram of the core. Branches are evaluated in the execute stage. So you already have kind of fetched 2 instructions. One is in the instruction decode stage and one is in the instruction fetch stage. And you have to throw away both of them and fetch a new instruction. That hurts because if a branch is not taken, it doesn't lose any cycles at all. Our idea is to decrease this penalty you have to pay when you are taking a branch. I mean, in the ideal case, if you're predicting very well and you do the branch prediction already in the instruction fetch stage, you don't lose any cycles for a branch.
Right, so I understand what the branch predictor would do, but my guess is that it's not going to buy you too much performance. I was just, looking for commentary on that. I mean, I can understand if it's like a 7-stage pipeline, but for a 2-stage pipeline, if you look at a standard x86 processor, this is, even if you get the branch right, that's the kind of penalty you would pay. I would estimate that you'd gain somewhere 2 to 3% in performance.
Yeah, I mean, we have to see. This is why we have to evaluate it first before just integrating something. I mean, if we're lucky and the integration is very simple, doesn't consume any area, and just gives you 2 or 3% of performance, I mean, that's fine. That's not a big deal. Just in the end, the overall picture has to be positive. Otherwise, we won't integrate something like a branch predictor.